Kia ora and welcome to video 4 in the series Delightful Differentiation. This video here is a pretty short one. We're looking at finding the coordinates of the stationary points or points of inflection. I guess that should read and. Points of inflection on the curve, y equals, now that's not cos to the -1, it's the arccos or inverse cosine function. Just to help you understand that if you've never seen the inverse functions before, the graph there is showing you cosine in blue and the inverse cosine in red with an axis of symmetry, the line y equals x.
Alrighty, in this video here, we've got two steps. We've got the inverse cosine function, which we need to differentiate twice. And it's not on the formula sheet, of course, and it also does not mean cosine x to the -1, because of course that is sec, or secant, the secant function. So -1 in there it's poor notation, but it means the inverse function of cosine. The function that you use when you try to find angles in trigonometry problems. And we need to show that the second derivative is equal to negative cotan times the first derivative squared. Bear in mind there's a difference here, that's the second derivative, but that there is dy dx all squared, different notation. And then we're using the result to find the coordinates of any stationary points and points of inflection. Okay, so y equals the inverse cosine. Because this is not on the formula sheet, we don't have a derivative table just to write down the derivative, and I haven't memorized it, so we're going to take the cosine of both sides, kind of like in video 1 how we logged both sides. We just rearrange it into a form that we can differentiate. Cosine y equals x. Now I could use implicit differentiation on this thing, as I've been doing in previous videos. It's a common theme of this week. However, I could just differentiate backwards, or upside down, so to speak. So if I've got x equals cosine of y, then I could just find dx dy. Okay, dx dy is going to be equal to negative sine of y. I don't need to put the dy dx factor like I normally do because I'm differentiating with respect to the dependent variable y. And then, what do I do here? I just flip it upside down. Dy dx, which is the thing I actually wanted, is equal to negative 1 over sine of y. I flip it upside down. Now that's a derivative in terms of y. If you're not happy with that, I guess you could take the actual y function and sub it into here. But not all functions can be rearranged to make y the subject. In this case we got given an explicit function, but in some cases you can't just do that. So having the derivative in terms of y, there's no problem with that. Okay, we actually want the second derivative. Now for this, I don't want to differentiate again with respect to y and then flip it. It doesn't work. I want to differentiate this with respect to x to find d squared y over dx squared. Now this is where I'm going to have to use implicit differentiation. Okay, negative 1 over sine y. I don't want to use the quotient rule for that if I've just got a constant at the top. So I can rewrite this as negative sine y to the -1. And then use the power rule and chain rule to differentiate, bearing in mind that I am differentiating with respect to x. So because the expression is in terms of y, it's an implicit expression, I need to use implicit differentiation. So the second derivative, using power rule, I drop the -1 down the front and it cancels off the other negative. I'm going to get sine y to the -2 multiplied by the inner derivative of this expression. The derivative of sine of y is cosine of y times dy dx. Okay, now what am I trying to aim for? Negative cotan times dy dx all squared. So I have to do a little bit of rearranging here. Dy dx all squared, I've already got a dy dx, so there's got to be another one in there somewhere. If I write this as cosine y over sine of y squared times dy dx. How's that going to help? Well, the cotan comes out because cotan is cosine over sine. So I've got cosine y over sine y. I steal one of the sine y's out of that bracket. multiplied by 1 over sine y, another sine y in the denominator, times dy dx. And that is cotan of y. 1 over sine y, well, that was the first derivative, well, almost the first derivative, right? It was minus 1 over sine y. But the thing we're going to prove has got a minus in the front, so we can pull that minus out the front and then times by negative 1 over sine y times dy dx, and then maybe make a note of it, something like by star, and we put a star next to the first derivative, and therefore it equals negative cotan of y times dy dx all squared. Proven. Okay, second part. Find the coordinates of stationary points and any points of inflection on the curve. So if you graph the inverse cosine function, let's just have a quick look at what it looks like. Y equals, I think it's a built-in function in Desmos, there it is, cosine inverse of x. Just, if you've never seen inverse functions before, let's just put in the actual cosine function there as well. You'll notice that the inverse cosine function's got a restricted domain, because the definition of a function is, well, a curve that only has one y value for any given x. So if you didn't restrict the domain and range on that function, you would end up crossing back over itself and having multiple y values for any given x. So if we look at what makes an inverse function, well, as expected, its x and y values are just inverse of each other. So you get that symmetry along the line y equals x, or sorry, about the line y equals x. On the red curve, which is the inverse function, 1, 0. On the blue curve, 0, 1. Yeah, it's just the x and the y values switched around. So if you ever want to find an inverse function of an expression, you just switch the x and y around, and then you've got it. You might have to rearrange it to make y the subject again, but that's how you do it. So looking at that inverse function, it's got no stationary points. There are no points on that curve where the gradient is 0. There are points where it looks like the gradient's undefined or tending towards infinity, but there are no stationary points. We need to prove that using calculus. There is a point of inflection though, right? Right in the middle is where it's its steepest. It's also where the concavity changes. It changes from concave up to concave down. So we're expecting a point of inflection right in the middle. Okay, let's look at the first derivative first. Stationary points. Stationary points, dy dx equals 0. What was our dy dx function? It was negative 1 over sine y. Dy dx equals negative 1 over sine y. Well, that doesn't equal 0 for any y. Okay, it's a fraction with a constant in the top. So 1 over anything is never going to be 0. So therefore, no stationary points. Okay, for points of inflection, we need to go about solving the second derivative equal to 0. And hence why the question has sent us towards the second derivative, but it's put it in this format because it's easier to use. So we have the second derivative. We want to solve it equal to 0. Now, when you do that, just a side note, when you solve the second derivative equal to 0, it doesn't mean you get points of inflection. If you don't understand what I mean by that, look at the graph of y equals x to the 4. When you differentiate that once, you get 4x cubed. When you differentiate that again, you get 12x squared. And if you solve this equal to 0, you go, hey, x equals 0 is a point of inflection. But it isn't. When you graph x to the 4, you get a minimum. Okay, there is no change of concavity at the point x equals 0. So to find a point of inflection, we solve the second derivative equal to 0, but it doesn't mean that the values we get are points of inflection. Alrighty. This thing equal to 0, well, this part is not 0, we've already said that, which means that it must come out of here. So, point of inflection if cotan of y equals 0, maybe, don't know, but cotan of y equals 0, well that's cos of y over sine of y equals 0, therefore cos of y equals 0. Of course sine of y can't be 0, but it won't be at the same value of y as cosine. Sine and cosine are out of phase. So y is equal to pi over 2. Okay, cosine of pi over 2 is equal to 0. Y is equal to pi over 2. Well, what does that mean about our function? We go all the way back to here, that will do. If y is equal to pi over 2, cos of pi over 2 is equal to 0. So x is equal to 0. We have a point of inflection at 0, comma pi over 2. Of course, there are other values where cosine of y equals 0. That has an infinite number of solutions, but there's only one in the restricted domain of our function. And range, sorry. We restricted the range as well. So point of inflection at 0, pi over 2. I would need to prove it. I think it would be suitable just to make a sketch of the thing and go concave up, concave down. But if you wanted to prove it using calculus, we would just look at the sign of the second derivative. Okay, the second derivative is equal to negative cotan of y times dy dx all squared. The part here is always greater than 0. We've already talked about how dy dx is never 0, so that therefore this part must be greater than 0. And so it really just depends on the sign of cotan of y. And you can argue that cotan of y means, well, what does the cotan graph look like? Let's just have a look at this. Let's change it to cotan. Hopefully it allows me to do that. Yep, so cotan there. Bearing in mind it's cotan of y, but it doesn't really matter about the variables. So to the left it's negative, to the right it's positive. So I'm thinking of y on that axis, but cotan look like that. If y is less than 0, then cotan of y is greater than 0. Y is greater than 0, and cotan of y is less than 0. But we have a negative in the front of that as well. So if y is less than 0, cotan's positive, there's a negative, so we get y dash dash is negative. Yep, that corresponds to here. That's and on that axis, very confusing, but on that axis it's y. So yeah, when y is less than 0, the second derivative is negative, and that's concave down. And the flip for y is greater than 0, the second derivative is greater than 0, that's concave up. All I'm doing there is giving a reason as to why it's a point of inflection. When there's a change of concavity about the point that you're considering, it is a point of inflection.